I want to welcome all of you to Beckman Laser Institute Laser Microbeam Program Seminar for this week. It's my pleasure to introduce Professor Stefan Cooper, who's in the Department of Chemistry and Physics at Alcorn State University, which is an HBCU located in Mississippi. Just by way of background, Stefan received his undergraduate degree in chemistry from the College of Charleston in South Carolina, and he did some undergraduate research there, working on creating derivatives of antibiotics. He then went to LSU and got his doctorate in organic chemistry. And he then had a couple different kind of postdoctoral appointments, one in the University of Maryland, and then later he was appointed as a kind of a special postdoctoral and pathway to the professoriate fellow at Hampton University. At Hampton, they have an NSF-sponsored program where they work with colleagues between Hampton University in Virginia and Brandeis University in Massachusetts on developing various types of functional materials. And then in 2017, he was appointed as assistant professor at Alcorn State. And today he'll be sharing some of his research with us. But I also want to mention that Stefan is also partnering with us. As many of you may know, Sari Mann and myself and Eric Patma co-lead a UCOP HBCU program where we bring very talented undergraduates from HBCUs to enjoy a summer research experience here. And Stefan is now a co-partner in that program. And so we're going to be having, hopefully we'll be having multiple undergraduates from Alcorn State participate in that program this summer. So with that, the title of Stefan's talk, a bit modified from the printed abstract, is preparation of a light activated template for selective Arene CH functionalization. Stefan, the floor is yours.
All right. I want to say first, thank you for that very, very kind introduction. And it's a pleasure and an honor today just to talk a little bit about the research that we are trying to do currently at Alcorn State. Just wanted to give a little bit of a slight disclaimer. First of all, my institution is particularly, or I would say it's majority undergraduate students. And currently we are in the phase of initiating our research project. So a lot of the slides and ideas today are just kind of the concepts that we are looking to explore in the lab. All right, so just for a little bit of background, in templated remote CH bond functionalization, there are two major players or two major research groups that we are standing on the shoulders of and trying to just kind of innovate some of the work currently done. Typically, the way that I summarize this to undergraduates is that this U molecular shape specializes in activating things at this meta position, and the D template shape specializes in activating hydrogens at the para position. All right, so typically template guided CH bond functionalization takes advantage of a strategic molecular shape, and they're going to be gained very favorable intermolecular distances to a desired hydrogen, and those hydrogens have the ability to be functionalized with the appropriate catalyst. So our work currently is in creating a C-shaped template, and we believe a C-shaped template will have some advantages to not activate only the para position, but also the meta and potentially the ortho position. But uniquely for our template is the ability to be activated with light. We'll kind of show that a little bit in today's talk. I apologize for the noise in the background and expect for students to be me at this point. All right. So there's two scaffolds that we are currently interested in exploring this idea of having a light activated template. The first is our Azo scaffold here. So in the ground state, obviously, I should say that we are comfortable with seeing that our Azo compound should adopt a trans conformation. However, with light, we are proposing this unique T-shaped conformation where this allows our substrate to kind of have this non-covalent pi stacking interaction that will allow us, if we can coordinate appropriately our metallic catalyst, to activate a hydrogen from our substrate. So this system has some unique features. Our atom X here are cleavable linkages to where we can easily attach any desired substrate and then be able to release that substrate upon functionalization. This dark area here on our scaffold is our metallic coordination site. So we are just kind of borrowing from the literature a lot of these different tethers that are already known to be able to coordinate to different metallic catalysts. And obviously here in the center, these are some of the substrates with the hydrogens that we are currently modeling to kind of be active, or we're modeling to be able to activate with our systems. On the opposite end of the spectrum, we're also interested in our Hydrazone scaffold. And from our Hydrazone scaffold, we feel as if that we could take advantage of, I guess, photosomerization to where we initially would have an opportunity to functionalize a meta CH bond, and upon shining light will induce a rotation of the hydrazone system here to where now we can activate at an oral position or ortho position, so sorry. And the idea here is just really trying to express that we can activate a different series or different groups of aldehydes. They can be electron poor, electron rich, they can be heterocyclic as well. And the whole idea here is that the chemistry to make a hydrazone is kind of in the realm of being click chemistry. We'll say it's very easy, it's kind of successful. So upon having the right hydrazone or functionalized hydrazine, we can easily prepare these hydrozones, activate at the desired position that's going to be toggled with light, and then we can hydrolyze off our hydrazine and we can regather back the aldehyde. And aldehydes are very great, or we'll say very convenient organic substrates, because you can oxidize to carboxylic acids, you can reduce down to alcohols, or you can keep the aldehyde as is. So this would be a really convenient way to also start to functionalize various positions with aldehyde substrates. Okay, so some of our unique features of the C-shaped template, I think we already kind of summarized some of those things here, is the advantage to be able to have this cleavable appendage. This T-shaped conformer, we'll talk more about that, but we're taking advantage of that from azo-heteroarenes. These are the potential substrates that we're interested in, and obviously if we have a carboxylate type of functionality here, that we can take advantage of that carboxylate assisted CH activation that's pretty prominent in the literature. Okay, so key to our AzoSwitches are is the azo-aeroherenes, or in that case here, this is the azo-aeropyrazole. All right, these are compounds that are known to have very unique conformations. Currently in the literature, they're referred to as having a T-shaped conformer. Depending on how you substitute your arene here, you can have a twisted T-shaped conformation as well. All right, so typically the wavelength of light currently is 365 is needed to be able to induce this excited T-shaped conformation. Interest to us for using it as a potential template for guiding CH bond functionalization are some of the features that are kind of very popular with these molecular photoswitches. They have very high quantum yields. All right, they have near quantitative photoswitching, and they have very long excited half-lives. All right, this is the reference here if anybody's interested in really following through with those. And these switches are pretty much right now in the literature very, very hot. I constantly get emails, alerts a day now with somebody, with a research group taking advantage of these switches in different applications. I'm so sorry that I wasn't able to summarize that today. It was my plan, just wasn't able to get around to that. So just to kind of tell guys that this is not chemistry beyond undergraduates, typically there are three main steps that we use in our research group currently to get access to these switches. We typically start off with a diet azotization. We start second with some type of alpha carbon coupling. In this case here, we have a diketone. And the last step here, you can take any hydrazine or hydrazide type of substrate, and you can cyclize into your pyrazole ring to gain access into the azo aero pyrazoles. Right. So typically we do the first two steps in a single pot, and then we'll do the third step in the second day. So typically it takes us about 2 days to generate access to our switches. So what we wanted to also show here is that this is, we're growing confident that this will be a great potential template by comparing some of our distances, intermolecular distances, with templates that are already published with ours that is pretty much we're publishing, not publishing now, but we're actually starting to work on now. If you look at the intermolecular distances between the desired hydrogen from a substrate to their metal coordinating site, the range is somewhere between 3 to 5 angstroms. And if you look at our proposed systems down here, we're getting somewhere close to about the same. We're getting about 3 to 4, 5 angstroms as well. So we're starting to grow very confident that upon everything else working right, coordinating the metal in the right site, and having the correct intermolecular distance, that we'll be able to activate those hydrogens. All right, so this is a summary slide, just trying to really reveal some of the advantages of having this photo switching auxiliary, or having a template that's activated by light. The first is that light now becomes a catalyst or a stimulus, and being able to govern CH functionalizations. We'll talk a little bit more about that, but that's obviously our first main advantage, is that now light is a key component in activating CH bonds, indirectly, I guess you would say. The second advantage is that the long half-lives that these molecular photoswitches have will allow us an opportunity to start to also think of pairing these systems with photocatalysts or other type of light-driven processes. The idea here is that you first excite your molecule, there's I guess the molecular photoswitch with the wavelength that it needs, and then take advantage of that light system to kind of add in a different wavelength of light that activates a different component of I guess you would say, a complex system here, to where now that convenience allows you to really play around with doing some unique chemistry. The third point that we wanted to also sell here is that we have this very planar base here, and being able to move around, in this sense here, our carboxylate tether from the para to the meta to the ortho position. We really feel like that's a nice, convenient way of enhancing or differentiating selectivity within a substrate. So in the case here, if we wanted to activate a para position in our, you said that we started off with the meta and it didn't really get us access, we can move to the para, or we can move to the ortho. Or if there's a substrate where there's a hydrogen bond that's pretty tough to reach, then we have this opportunity to kind of move things around to see if we can model or have an opportunity to activate that CH bond. But at the same time, having this feature definitely allows you to activate different hydrogens on a substrate, right? Carbon hydrogen bonds. And the last thing here, which is probably our most radical idea, is the opportunity to do this regio divergent or regio selectivity that is toggle select, I guess exclusively by wavelength modulation. So the idea here is the fact that now we can activate different hydrogens by tuning different wavelengths of light. And I have a different slide, or another slide, that we can kind of showcase that idea. But as a whole, these four main advantages are what we're trying to really, I guess, secure and really trying to advertise as an advantage of having this approach to doing templated guided CH bond functionalization. So with the regio selectivity here, the azo component is already known and well published director at the ortho position. So if you have the ground state molecule and you add in just your typical palladium catalyst with the right ligand systems, the azo will coordinate to that palladium, and then you would functionalize at the ortho position. What we're proposing initially is that if you activate this molecule now to adopt this T-shaped conformer, and you're able to potentially coordinate your metal to where it has access to remote CH bonds, then we think that this is a great opportunity to start to do some of that regional selectivity. With no light, we can activate ortho hydrogens, but with light, we start to get remote CH bond functionalization. All right. The second idea here is to take a bis azo substrate and have those two azo substrates kind of designed where there's a metal coordinating functionality in a metal position up top here, and here in blue on the bottom we have our thiol position in the para position. And so we tune this blue switch, or the blue azo compound, to a longer wavelength, and so we shine that longer wavelength onto the molecule, it adopts the conformation, and we can activate it at the para position. But then we take our carboxylic or carboxylate switch at a shorter wavelength, we activate it, and now it adopts a conformation where it can activate at the para position. So this allows us to take a single or the same substrate and be able to activate at different positions, all by just tuning to different wavelengths of light to be able to facilitate that activation. We're trying to sell that with a really conscious and clever strategies. I'm pretty sure this could be helpful in the construction of very important and desired functionalized materials. All right, so our last kind of important idea in our research group is the ability to have redshifted azo heteroarenes. The idea here to have something that's redshifted lies initially in the need of having molecules that are accessible for biological systems or within the biomedical window. But also within our group, we need this idea to be able to build a library of photoswitches or azo molecular photoswitches that are operable at different wavelengths. And so just looking through the literature here is that if you wanted to take advantage of the strategy of coordinating a Lewis acid to the azo, there's two potential coordination modes if you have atoms that can help chelate in your Lewis acid. You can generate the 6-membrane chelate or the 5-membrane chelate. And from the 6-membrane chelate, there are reported systems that have a nice redshifted absorbance. However, this molecule does not have the ability to photoswitch. All right, so we like to call this in our research group this endocyclic azo ring. So whenever both nitrogens are participating or atoms within this 6-member ring, they do not have the ability to photoswitch. On the opposite end, if you are able to form the 5-member chelate here, you can generate potentially a exocyclic ring here, and this affords one of the nitrogens to be not inside of this Lewis acid chelate, or cyclic, you would say cycle here. And this moiety here retains its ability to photoswitch. All right, so something that's indirectly an interest to us is the ability to redshift absorbance, but also to retain the photo switchability of the azo photo switch. And currently we're finding that this T-shaped conformation is becoming very important for us to be able to control this type of coordination. The 6-member ring is thermodynamically stable, and typically it's the most common type of mode of coordination with Lewis acids. However, we're experiencing opportunities to build these type of systems, taking advantage of that excited conformation that affords the 6-member ring, and not easily prepared, I guess to say. Okay, I would like to end with acknowledgements. This is just kind of a summary of the research group. The 3 students here in the upper left-hand corner are my 3 initial research students. It's kind of sad to say this at this point. They're at the point where they're getting ready to graduate from Alcorn, but they were key students and just volunteering to help prepare some of the systems and run some of the UV-Vis experiments. The spring of 2020, right before COVID, I had a pretty big research group. We're really trying to move forward with this preparing diverse libraries of Azo photo switches. We're looking forward to confirming their confirmations and trying to start to hook up 10 different desired substrates and add in and start screening, I guess, conditions for CH bond activation. And currently here in the center right screen of the right-hand side of the screen are my current 5 research students. You can see that we're trying to say stay in the lab with our masters and things of that. But we're looking forward to advancing the work and still trying to pursue our initial thoughts in a template or a light activated template for remote CH bond functionalization. Currently, I don't have any work on the Hydrazone side to talk about right now, but we're also getting some students on the Hydrazones. Particularly, all students on the screen have been working exclusively with the Azo PowerZones systems. So just for a summary, and this is coming just from a teaching background, I wanted to make sure I try to summarize the thoughts, is that we're hoping to have a novel light activated template, and we're focusing right now on Arene CH bonds. Okay, so we have 2 systems in mind to kind of do this work, the Azo and the Hydrazone. And then we wanted to sell the novelty of the approach. That's kind of currently what we are facing with reviewers and things of that. What is the main advantage of photo switching in solution? And we really think that not only we get access to remote CH bonds through that unique T-shaped conformation, we think that having that planar base allows us an opportunity to enhance selectivity by moving that coordinating atom or coordinating site for the catalyst. And lastly, we think that having the ability to tap into light allows us to do this regional divergence of activating CH bonds that is exclusively modulated by light wavelength. Right? So just to kind of to summarize things again, this is a summary slide. We're a research group in the heart of Southwest Mississippi. We are a new research group, and we are interested in pursuing an idea in light activated templates. And these are the 2 systems that we're currently interested in utilizing. And I'd like to say again to the facilitators of this symposium, and to also to all of those that are currently listening, a big thank you for just taking the opportunity to listen in on some of the work and ideas that we're trying to pursue here at Alcorn State. Thank you.
Thank you, Stefan, for your presentation. We can, of course, give him a virtual round of applause. And this talk is open for questions. I think it's probably, you can either raise your hand or you can just, unmute yourself and speak up.
Hi, I have a question.
Yeah, sure.
Very nice talk. Thank you. So
Thank you.
I wonder if you can comment on the reversibility of your photo switches. You said you had more work on the Azo, and I wonder with the regio selectivity is very interesting, and I wonder with the substituent groups that you're attaching, does that affect the reversibility of the switching?
Yeah.
Does that affect the switching efficiency?
Yes, that's a really good question. Something that we're building a catalog of different things that doesn't photo switch right now currently. So that's a big issue. It looks like right now in our systems is that if we have something very big and planar, we need like a methylene group in between the nitrogen and the arrow group. So that's probably something that didn't. I tried to capture that in maybe some of my initial substrates. But if we attach the phenyl ring directly to the nitrogen, there's some issues in the photo switching. Obviously, if the sterics is too big here as well, there's some issues there. But the silicon atom is large enough where the distance isn't as bad. So we're realizing that it looks like it photo switches. But some of the ideas here as well is that we need to start to understand concentrations and the power of the light source that we're using. We're currently just using very low power LEDs, but we're hoping that if we can start to understand what concentration works with our LEDs, that'll be great. But if we have access to a stronger wavelength of light, maybe something like a laser at the Bateman lab, that could be something that could really activate more of our molecules. We can experience that. Yeah. So the
Thank
light
you.
source, yeah, good question. We're a little limited with the light sources right now.
Although maybe just a follow-up, you mentioned about the light source. I wonder, and you said right now you're only dealing with lower energy light sources, but I wonder if you use a laser, for example, for the excitation, do you think that that might cause your sample to decompose?
It could, yes, definitely. Probably there's a fine balance between the right concentration and the right wavelength of light. That's a good question. In the literature, I mean, even right now, I'm trying to really distill that type of information from literature. There's not a lot of discussion about that. How much power you need. I'm just copying a lot of the procedures that most researchers use, which are just common UV lamps that you use just for TLC type of stuff, or the variant LEDs. I haven't seen anybody publish anything yet with laser sources. So that could be the major concern is the power of that.
Yeah.
But hopefully.
Thank you.
Yeah, no problem. Thank you. That's a great question.
Other questions for Stefan? So Stefan, when you were developing these tools initially, was there a particular application in mind? I guess, for those of us, myself, who are not chemists, I want to kind of better appreciate kind of what functionality this provides for potential applications.
Yeah, that's a really great question. And that's a question I probably don't do the best of a job of really explaining. The direct application is to really try to get into molecules that have very high usage in pharmaceutical or agricultural type of uses. So I'm sorry to say this. This is something my students are thinking the same way. Like, do you know of a drug molecule that we can make and things of that? And I'm really interested more in the methodology. I'm kind of in the core of the mindset of just really methodology. So I really just wanted to showcase that we can build from very common and very cheap heterocycle cores, highly functionalized materials, right? So you can imagine maybe starting off with some type of pyrazole ring, and then we can make a 2-chloro to bromo exclusively from just hooking it up to our photo switch, tuning the light switch, and then detaching it off, right?
Understood. So basically you're creating new technologies to synthesize new compounds.
Exactly. And the goal really as well is to even tap into very crude materials from petroleum. So things that are very simple, and we can start to selectively activate those hydrogens in crude petroleum, and then we can sell highly functional, or not, I'm not saying we're selling, but we can sell the idea that you can take crude, cheap petroleum, activate, and build very complex substrates from that.
So you start from very cheap feedstock and you're able to
exactly. And tapping into the carbon hydrogen bond really allows you to be able to do that type of chemistry.
Thank you.
Hi, Stefan. I had a kind of follow-up question for Watson's. The photo switching, what exactly that kind of property can be used for, biomedical applications? Is there any link between that? Because we're familiar with photodynamic, but not very familiar with the photo switching.
Photo switching. Yeah, no, thank you. That's a good question. Yes, there's an idea that we have in the background. I'm too afraid to start to showcase that today, but it really comes in functional materials. There's some ideas that were started as a postdoc where we were using photo switching materials to build an amplifier that if you can have it self-assemble into a mind cell, that you can shine light and use it as a drug carrier in a drug delivery system. So I think initially those are some of the ideas is to take advantage of self-assembling, where you can pre-organize a drug and then shine light to where you can release it due to the photo switching ability of the amplifier. Yeah.
I see.
There's a couple of groups that do things like that. I think this will be a great opportunity to take advantage of a switch that has that T shape. So there could be some unique dynamics there versus the current models that are published.
Thank you.
Stefan, you indicated, oh, sorry.
Please.
You indicated that there was some sort of flexibility in the wavelength that you could use for this. Can you talk about that a little bit more? What sort of range of wavelengths can you use?
Yeah, that's a good question. We're still building the systems. A lot of the ideas are coming from the models, but I can kind of try to best summarize like this, I guess, in a sense. So we realized that if we have like so our wavelength modulation comes from just different electronics on the rings. So we have a system that we're trying to build now where we have like, we make the parallel ring very electron rich. So we have like a methoxy group in one position. And then we have our benzene ring electron poor. So we try to have some type of electron withdrawing group. And that has an opportunity to tune the wavelength away from 365. Typically that's gonna be a little bit redshifted. And other switches, if we make both rings pretty electron rich, they seem to sit right at 365. But ultimately, our main goal in really differentiating between wavelengths is this coordinating to the azo. So typically, whenever a Lewis acid coordinates in, you make that bond a little bit longer, the nitrogen bond typically longer. And for most cases, those systems are redshifted from 365. So again, we'll take advantage of that to move it from 365 and then build some different electronics around to start to have different switches that are operable, different ranges. I guess I think we've seen a number around 500, but that's probably as redshifted as we've got so far. So we went from at least from 365 in our initial systems to around 450, 500 range right now. And that's just playing around with the electronics on the ring so far.
So this is right in the visible region then, really, between about 300
Yes.
and 500.
Yeah, that's right. That's right. We're hoping to, the goal obviously for our group is to get somewhere at 600, 700, and we can really tap into something that could move into the near IR range. That will be the goal for biomedical interest. But we're nowhere near there right now. Nowhere near.
Yeah, I could see that would take a lot of work.
Yes, sir.
All right, thank you.
No problem. Thank you.
Any further questions for Stefan? So let me just thank Stefan for a very stimulating presentation. I also just want to reach out and just let everyone know that, as part of our program that we have with Alcorn State, that, we hope to be able to bring Stefan or other of his colleagues out to experience kind of the research environment here at UCI. And so to the degree that people might be interested in collaborating with Stefan, you should feel free to reach out to him. If you need his contact information, reach out to me. And I'm sure Stefan would be interested in hearing potential synergies between your research activities and his research group. So with that, let's again give Stefan a virtual round of applause. And I imagine that, if you want to have kind of a more close discussion with him, you can virtually walk up to his podium and ask him a few questions with a smaller group present in a minute or so after people stream out. So thank you again, Stefan. We really appreciate the willingness for you to come out and speak to us about your research.
Thank you. Thank you.
Thank you.
Thank you.